So today we will be going to discuss Bayesian learning. The first topic is map hypothesis. Like you already know what is hypothesis, but I want to define it precisely so that you can understand what is it. You learned right. Machine learning is interested in the best hypothesis H from some space capital H given observed training data. So, for an example, I want to learn some function, uh, that function that can accurately describe the data. So I could have like a space where there are a lot of functions or lot of hypotheses are available, and I want to choose that function from this space. This space is capital H. I want to choose one of the function, the best probable function that describe my data, right? For an example, if my data is this, so this is the line that describe my data very perfectly. So in this space capital H, there, and if this line is also available in this space, then my task is to find out the hypothesis among all the hypotheses given in this space that describe my data perfectly or accurately or probably most likely, I would say. So this is that one. So machine learning is interested in the best hypothesis H from some space capital H given observed training data. That's what I described. So best hypothesis is most probable hypothesis. It may be possible that the hypothesis available in the space may not describe the data perfectly. For an example, if I would have a data point here also and here also, so there is no perfect line, or for example, if my hypothesis space only contains lines only, so there is no perfect line that can go through all these points. So what is that probable line that can best describe my data? So my intention is to find out that hypothesis. How I'm doing it? So Bayes theorem provides a direct method of calculating the probability of such hypothesis based on its prior probability, the probability of observing various data given the hypothesis, and observed data itself. So there are three terms. You already familiar with all these three terms. This is the prior probability, like what are the chances that this may happen. Some hypothesis in a space. For an example, this is H1. This hypothesis is H2. This hypothesis is H3. This hypothesis is, let's say, H4. So there are, let's say, four hypotheses. So what are the prior probability of choosing the hypothesis from this space? In case if you don't have any idea what could be the probable hypothesis, you can choose any of them, and in that case, each hypothesis having an equal probability in that case. But if you prefer one hypothesis over the other, then there would be some some notation or distribution over this space. The distribution, what I mean to say, for an example, let's say somebody says that H3 is most probable, then H1 is most probable, then H2 is this, the probability of H2 is this, then H3 probability is this, and H4 this probability is this, and the sum of all these probabilities must be equal to 1, right? So now you can see that the prior probability of choosing any hypothesis H1, H2, H3, and H4 is decided by this prior probability. So according to the prior probability, my highest probability of choosing a hypothesis is H3. But if you don't have any idea how to choose the prior probability from the space, then you can, most of the time, you can say that every hypothesis in the space is equally probable. In that case, the probability for hypothesis will be 1 upon n, and n is the number of hypotheses in the space. In case I am having a finite hypothesis in the space, we will see what is infinite. So I'm just trying to describe, trying to explain what is prior probability and how can we take that measure of prior probability. For example, in finite space, if you feel that there is a mm, that every hypothesis is equally probable, then you can divide, then you can take the probability equals to 1 by n, and n is the number of probability in the space. So pH is this prior probability. Now the other probability is what is the probability of data given h. What is the probability of data given h? Now you choose some hypothesis from the space. Now how best that hypothesis is describing the data. For an example, this is the case, this is my h3. Let's say this is my h3, right? And this line is this one. Let's say this is h2. So now the probability of describing if this is h1, let's say, or h3, let's say. So now the probability of data given h3 and the probability of data given h2, you can see intuitively from here that h3 is more closer to data points in a space than h2. So in that case, the probability of seeing the data given this hypothesis is more than this probability. It means what is the probability of seeing the data when this hypothesis is given, and this is what is the probability of seeing the data this hypothesis is given. In this case, we can see this number is bigger because it is more closer to h3. And the third term is what is the probability of data itself, right? So in this equation, you can see the probability of data is inversely proportional to the posterior probability, that we say this probability. It means the more you have. What is hypothesis span? Can you please give me an example? So Ame is asking what is hypothesis. Can you please give an example? So hypothesis I already gave in the first lecture. So what is hypothesis means? For an example, somebody told you that there is the only possibility that you can fit a line to a data. So let's say this is a data given to you, and somebody said that you have to choose only a line to describe this data. Now the hypothesis space for you will be the infinite lines in 2D plane. And infinite lines in 2D plane, let's say this is a 2D plane. So this could be a line, 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 this could be a line. Any of the line is a hypothesis here. So my task is to find that line, means to say that hypothesis that can describe this data perfectly, right? So here what I was saying that this is the PD, inversely proportional to this posterior probability. What do you mean by inversely proportional? What exactly it means intuitively? So PD means that if it is greater, as big it is, the less this number will be. What do you mean by to say? For an example, now the probability of seeing the data independent of any hypothesis, if it is very large, then obviously no hypothesis has produced that, right? Produced that data. Now no hypothesis can produce the data. So if it means the data is independent to any hypothesis. Now you are trying to find out, given the data, what is the probability of this hypothesis. Now I am saying that probability of data is independent of any hypothesis. Now how can you say that now this number, that probability of hypothesis given data should be very less, because PD is independent of any hypothesis. So map hypothesis, just it is the same thing I told you, like I have repeated it in number of times in different lectures so far. I have discussed from the day one to this day. But formally, what you have to say, in many learning scenarios, the learner considers some of the candidate hypothesis H. Candidate hypothesis H, let's that what I have given the example. Let you maybe that candidate hypothesis is a line. So there could be infinite line and 2D plane. So your here candidate hypotheses are line in a 2D plane, and is interested in finding the most probable hypothesis H given the observing training data. I explained it very clearly in the previous slide. Any maximal probable hypothesis is called maximum a posterior hypothesis. So your task, this is what you are calculating. It is nothing but using Bayes theorem. You can expand it like this. This is independent. PD is just a denominator, right? So PD is just a denominator. You can ignore it because it is independent of H. Now your final task is to maximize this expression. So you take every hypothesis from the space one by one. For an example, these are infinite lines in a 2D plane, and this is the data you have, data given to you. You take one line one by one. Let's say you take this line. So this line is this. You find out the probability, the prior probability. Let's say the prior probability of all these are equal. So in that case, there are 100 lines there. Let's say. So I'm saying my prior probability of picking any line is 1 by 100. Now, what is the probability of D given H? So you have to calculate it from the data. Let's say the probability by seeing it, this probability is less than the probability of seeing this line. Obviously, when you multiply the prior probability with this line will be greater for this line in respect of this line. So your task is to calculate this expression for every hypothesis, and this argmax will give you that hypothesis which makes this expression the largest one, the numerically the what is the largest probability you will get. So one question is, so when we say no hypothesis fitting the data, it means there is no H in the space which fits the data. So that this is a theoretical question, and what I would say, because you don't know a true function, right? Right now I'm saying that that this is the data that could be generated from a line. In this case, you know this is generated from line, but somebody gave you some random data, and this data is like this. Now you don't know how this data is generated from which function. So you cannot say whether the line can generate it or the function can generate it. You don't know the true function of it. So in that case, you try to maximize, you try to consider as larger hypothesis set so that it may maximize the probability of having the exact true function in that candidate set. So you can never say that whether their true function is present in that hypothesis set or not, right? Yeah, so the question is, what if hypothesis is not a line? That's the same way I told you. You cannot say the hypothesis. I'm just explaining you that it could be a line, but it could not be a line also. It could be a function. It could be a M order function, as we discussed in linear regression, right? So in that case, the larger hypothesis set you will consider, the probability of getting the true function from that set is more, right? If you say this is the data that you want to fit, and let's say you know the true function, for example, this is the true function. Now somebody come and ask you to what is the line that is fitting to the data. Now you are considering the capital H is only the lines, right, in 2D plane. So you can never find this hypothesis is here because this hypothesis does not contain in this set. To maximize the probability, because line is the order of like W0 plus Wx1, right? Wx. Now to maximize the probability that you can see that you can have the true function in your data set, you just increase the order of this. Now this is a quadratic. Now you have this kind of function also. Sorry, this kind of function also in your hypothesis data set, but still you don't know whether because this is a cubic order function, right? So in that case you further maximize your hypothesis set, and this is Wx cube. Now your hypothesis set will also contain this true function. One by one you take this hypothesis. First you take line, every line you tried, then every quadratic line you tried, then every cubic function you tried. Finally you find out, like, among all the hypotheses, this cubic function is fitting the best. So that's how you find out this. So is PD given H means error function? No sir. PD given H means that This is my hypothesis, right? So what is the probability that some hypothesis is given to you and that hypothesis can generate the data? For an example, this is my hypothesis and this is the data. So this is the data. So what is the probability? Let's say this is H1 and this is H2. So this is H2. So to PD given H1 means what is the probability of this data, these 3 points, of seeing this data given H1 hypothesis. So this is H1 hypothesis. The probability, let's say there is some probability that H1 is given. What is the probability that you can produce this data using this H1? So let's say there is some probability, but intuitively you can say that the probability of data given H2, that if H2 is given, then you can produce the data with using this H2 is greater than obviously when these two hypotheses are given. So what this is what PD given H means. It means what is the likelihood to see the data given hypothesis. So there could be a different likelihood, right? So uh, so one question is from one student: we might overfitting problem with higher degree equation. Then what should we consider? So yeah, that is again I explained in my previous lectures. When you just go through that lecture once again, you will have a better idea. But because always you try to you try to consider that set which will have your true function in that. In that effort you will always try to fit the data more closely, and that will help that will result in a overfitting. To avoid overfitting, you have to consider, you have to apply regularization. And regularization, I told you what regularization is. Sorry, right now I cannot explain, but you should see those previous lectures. Regularization, I told you, I explained very clearly in that linear regression chapter, linear regression lecture. I cannot recall what it is. So uh, so this sometime it is assumed that every hypothesis is equally probable, right? In this case, the equation above can be simplified, because if every because if every h is having a same number, let's say 1 upon n, 1 upon n, and the number of hypotheses in the space. So pH1, pH2, also 1 by n, pH3. When you sum all these phi, you can say 1 upon n plus 1 upon n, and there are n terms, right? And when you sum it, it is by n, and it is a 1 in number. So yeah. So what I'm trying to say, that whenever you multiply this number with pH, some probability, all the hypotheses having the same number for it, some same probability, so this term will not affect this expression finally. So you can avoid this also, and ultimately you have to maximize this thing only, that is called the likelihood thing. So the probability of seeing the data given the hypothesis, you want to maximize this probability. You want to maximize this probability mean to say you want to pick that hypothesis from the space that the probability of seeing the data from by using that hypothesis is more is larger among all the hypotheses. So in likelihood case, the prior probability, we assume that all are equal in number. So all are equal. So we can ignore it, and finally the expression that we left that we have now, we can say that is a likelihood expression, and the maximum of it, maximum of the likelihood is called the maximum likelihood hypothesis. So pH can be dropped because it is equal for every h. I told you. So this is the same example I already take it in the yesterday's lecture the first, but just for your sake, just to I thought to repeat someone again. There is some medical diagnosis problem is where there are two alternative hypotheses. So the patient has particular form of cancer and the particular does not. So the cancer may be present and the cancer may not be present. The available data is from particular laboratory with two possible outcome. So you go to the for example, you want to test whether you have a cancer or not. You go to the laboratory and test yourself, and that there could be two possibility that come. Either you can have a positive, or you could have a negative result towards your disease. So now the probability of the seeing the cancer in a population is 0.008. You can see it is a very less probability, like a 1 in 8 in 1000. If you have 1000 person, only 8 are having a probability of having a cancer in that population. Of not having a cancer is 1 minus of this p. And this data is, once you have a cancer, you go to a doctor for a test, then the probability of having the positive result is 0.98. It means the test is not accurate. It is accurate only 98%. When you have a cancer, you could go for a medical check. That positive will say you that you have a 0.98% probability. If you have a cancer, you go to the doctor for a checkup. He say no to you with probability by this 0.02. This comes by 1 minus 0.98. Similarly, when you don't have a cancer, so this is one test. So this is a second probability. When you don't have a cancer, you go to the doctor, you see the medical report, and you find that you are positive. This is very less likely. 0.03. And when you don't have a cancer, you go to the doctor and you find negative result, that is highly likely, 0.97. Just to find out what is that, once you have a given result is positive, what is the chances that you are having actually a cancer? That's what I want to find out. By expanding the Bayes theorem, I can write it probability of having positive cancer, probability of cancer upon probability of positive. I already explained in the, you can ignore this expression because it is constant and it appears both in case of positive and negative. Finally, you have to evaluate this expression. You fit it into, you just substitute into the form of this expression. You got 0.0078, 0.298. Finally, what this hypothesis maxima a priori is saying, that you are not having a cancer. So you go to the you go to the laboratory, you find out that the test is positive. So using this data and using Bayes theorem, once you find out that the test is positive, what is the probability that you are actually suffering from a cancer? The probability that you are suffering from actually from a cancer is proportional to this expression. And from here you can say that for having not cancer is high. So this is 0.298. If you want to convert into the terms of probability that you are having a cancer, is that multiplication, and you will normalize it by the sum of both these. This is 0.0078. This is this. So this is 0.0078, and this 0.009 term is this. So this is a constant expression. It will not finally change the order like maximum or less than. So from here you can say, when you find that you are having a cancer, that the test is positive, the probability that of having a cancer is only 0.21. And the probability that when the test is positive, the probability that you are not having a cancer is 0.789. It is very larger than this number. From where you can say that if you have to choose one of them, so you can say that no, I am not suffering from a cancer, though the result is positive. But the thing to be observed here is the probability of having a cancer. The prior probability was 0.008. But when the test is result, so it makes you to believe more now that you are suffering from cancer. At first, when you didn't have any test, you didn't have any data or evidences with you, the probability of you to having a cancer is only 0.008. That is a prior probability that is equal for every person. But once you go to a doctor, you test yourself, you find that yeah, that test is positive. Now that number increased from 0.008 to 0.21, and you can see that this is greater in magnitude of like 10. or multiplication of 10. So the more evidences you get, the more probability it will be increased over. So you that's what I meant to say. The prior probability at first when you don't have test, and the probability when you have a test, the evidences will make you more believe in having the disease in you now. What is the relationship between, so concept, I use the term concept learning because it is used in a book. Though when you read the chapter 6 of Tom Mitchell, you will find these same terms there, and I don't want you to be get confused in that, so that's why I use those same terms. But concept means function here. So whatever the function I'm trying to learn from the given from the hypothesis space, this is the H, right? And there are number of hypotheses available in this capital H. So my true function is, let's say this is my true function. So I'm trying to learn the concept. The term learn the concept means this is my true function. I'm trying to learn this function from let's say from some algorithm, or say we will see how we can learn this. So what is the relation between Bayes theorem and the learning of function? So as we did in the curve fitting, how we come up with the cubic function, maximum likelihood we find out sum of roots, sum of square, were minimizing the error terms, and finally we come up with a hypothesis that is most probable. So what is the relation between the Bayes theorem and the function or concept learning or curve fitting, I would say? So what it can be used for designing a straightforward learning algorithm. How can we use to find out a straightforward algorithm? So there is one algorithm. First, let's understand what it is, and then I will relate it to. So there is a, for each hypothesis, H calculate the posterior probability. You know what it is. I don't have to go tell you again and again. Map also, you know, maximum a priori. Sorry, maximum posterior. And here PH given D. So posterior probability, we assume that everybody is having the same so same prior probability. In that case, this H map is equals to this expression. Sorry, sorry. So this is H map means the hypothesis that is maximizing this expression. The maximizing this expression means maximizing this whole expression. So the hypothesis that's maximizing this expression is my H map. That is the most probable hypothesis. So in order to specify a learning problem for algorithm, so this is example. Just go with just walk through this example with me, and I will conclude what I want to say with this example, so that you don't get confused while reading the book. So I have a data set that is noise free. First thing is it is noise free. If I want to fit a data to a line, let's say somebody said that this is the data generated by a line. Now I know that this is a noise free. So obviously there never I can find these 3 points, because if it is noise free and I know that I have to fit the line, so because line cannot go through these 3 points, so there must not be a noise. So noise free data in this case will be this. I can perfectly go through these 2 points or these 3 points. So the training data is noise free. I don't have any noise in it. Target concept C is contained in H. So as somebody asked in previous slide, what if the H is not there in that space? So sir, here we have to assume that the C is the function we are trying to learn is available actually in the hypothesis space. So second assumption is first assumption is data is noise free. Second assumption is that the function that we are trying to learn is actually available in the hypothesis space. No reason to believe that any hypothesis is more probable than any other. So what I mean to say that prior probability of every hypothesis is equal, and in this case this is a cardinality expression. In set theory, if you see these notation, it means the number of items in this set. So this is the H hypothesis space, and there are different, let's say these are the three hypotheses in this space. So the cardinality of H is equals to 3. Well, the number of hypotheses in this set. So PH is equals to 1 upon this number of hypotheses. So for example, if it is N, so it is 1 upon N. It is equal, right? And because I said that the data is noise free, and Data is noise free. First assumption is that. And second assumption that C is available in a hypothesis set. It means I definitely have that hypothesis that can produce my data perfectly because it is noise free, right? In that case, if I choose that hypothesis which actually produce my data of seeing the data is 1, and if I choose a hypothesis that cannot produce my data, in that case the probability of seeing the data is 0. This is because the data is noise free. For an example, this is the data and it is noise free. I know that the corresponding line is available in this hypothesis space. Now, if I choose this line, if I choose this line, I know that using this line I can produce the data. I can see the data. The probability when somebody tells me that this is a line, what is the probability that you can see the data? It is 1 now because the data is noise free. And if somebody should give me this line and this line, what is the probability that I see this data using this line, or I can produce the data using this line? This is 0, right? So this is what this term is saying. So what it is? Hello sir, could you please send us upload these PPTs in portal? What do you mean by annotated PPTs? Like what I'm writing on it? That's one. So these PPTs are there. Okay. So I will ask them to upload these PPTs what I'm using in this lecture. So, sir, one question from Nidhi is, isn't this algorithm talking of the ideal scenario? Yeah, it is talking about the ideal scenario, like noise-free data, target concept in Israel. Yeah, it is talking about the ideal scenario. But I will relate it to why we are learning it and why I'm trying to explain it. Also, there are no recorded lectures. So first clear me this. Somebody is saying that there are no recorded lectures there. I'm seeing myself there are recorded lectures available there. I don't know why you're not finding it. So I will discuss this point after this lecture, right? Does this course don't have any recording sessions? Yeah, this is having a recording sessions. It is available on the portal. You can go and see it. So I will take these questions afterward this lecture. So just first let me complete this lecture first, right? So because it will break this. So Nidhi was asking, doesn't it? Isn't it an ideal scenario? Yeah, it is an ideal scenario, but I will let you know why I'm trying. Why not I am? Why Tom Michel is using this example in his book, and how he's relating to the concept. So now the problem for learning is fully defined, right? In first step, we have to determine the probabilities of P H given D. So now if H is inconsistent, I know if H is consistent, then the probability of seeing the data with that hypothesis. Inconsistent means here inconsistent means that it cannot produce the data. If using the hypothesis, what is the probability I see the data? So inconsistent means it cannot do that. So H is inconsistent with the training data. It means that the probability when H is inconsistent of seeing the data is 0 because it cannot produce that. So this 0 is equals because of this. And whatever these numbers doesn't make the difference because 0 multiplied by 0 divided by some number is equals to 0. So all the inconsistent hypothesis will have the 0 probability now, and all the consistent hypothesis in the space, it may be possible. Just to let you know, just little broaden your mind and try to think this example. For an example, you have these 3 points, and I say that just fit the hypothesis to these 3 points from this space. So it is have a cubic function, it is a quadratic function, it is having a cubic function, and let's say it is having some n order function also. So in that case, I can fit quadratic function also, I can fit cubic function also. I don't know how to fit it. let's say this is a cubic function, and let's say an order function. So here in this set, it may be possible in a given hypothesis space, I can fit the data to the hypothesis that are more in number, more than one. It is not always that I can fit only one hypothesis to a data. It may be possible that I can have a multiple hypothesis that can fit the data. As we had seen that in that logistic regression class, there was a curve, and we fitted perfectly the order of ninth polynomial there. So H is consistent. From this line, you can understand, what you can visualize, or what you can take is H is consistent with training data, means H can produce the training data. So if H can produce the data, then probability of seeing the data given H is equals to 1 in this case. If H is consistent, it can produce the data, and therefore the probability is 1. And the prior probability is 1 by H. I already told you. What is this PD by H? What is the probability of seeing the data? Now from here you can also understand what is actually PD means. So I told you that there could be multiple hypotheses. So one hypothesis, let's say H1, so the one hypothesis is H1 that can produce the data, other hypothesis H50 that can produce the data, other hypothesis H30 that can produce the data, and there are 100 hypotheses in the space, let's say, from H1 to H100. So only 3 hypotheses can produce the data. What is the likelihood, not likelihood, what is the probability that I see the data in general without considering the hypothesis? So that is 3 by 100. The probability that I see the data by H1 is 1 by 100. The probability that I will see the data by H2 is 0 by 100. The probability of seeing the data by H3 is 0 by 100. And like by when H30 comes, it by 1 by 100. And the probability, these are the prior probabilities, right? And these H50 is 1 by 100. So finally, the probability of seeing the data independent of hypothesis is those hypotheses which actually are consistent with the data divided by the total hypothesis in the space. So this Vs is the version space. Version space means all the hypotheses that are consistent in the given space H. All the hypotheses that are consistent with the data in a given hypothesis space H. So this is version space. So now when you put this expression and simplify it, this H gets cancelled with this H, and finally you get this 1 by H. So with a simple example, if somebody is saying what is the probability that some data is given to you to see a particular hypothesis, so I know that there are only 3 hypotheses that are consistent in this example. So if there are only 3 hypotheses that are consistent in this example, then one of the hypotheses might have produced the data. So because in that case 1 over 3, if you take any of the 3, now this is 3 hypotheses that are consistent, H1, H50 and H30, right? So there are 3 hypotheses, and because the chances to see the data is one of them may produce, the probability for this one that may produce is 1 by 3, the probability of this may produce the data is 1 by 3, and the probability of this produce 1 by 3. So that's why it is 1 by version space. Version space means all those probabilities that are consistent with the data. So Vanna, you please, I think we will be short of lecture. I will take this this question later. So Vanna is asking, sir, can you explain PD again? So PD is nothing but the probability of seeing the data. For an example, you might be confused because you are not be familiar with this concept. For an example, there are 4 events: A1, A2, A3, A4. So there are 4 events, right? Somebody said that what is the probability, and this is the event V. This is the event B. What is the probability that you see this event B only? This is the event B. So you can see this event B is having overlap with A2, This event B is having overlap with A3. This event B is having overlap A4. So this event B is having overlap with every year. Now somebody is asking me what is the probability of B? What is the probability of B? So the probability of B is this sum plus this sum plus this sum plus this sum. So when you add all these numbers, all these four numbers, so this is the probability that you see the data, see the B event, independent of any other event. This B is telling you the probability only to see the B event, irrespective whether it is generated by A, whether it is generated by A2, A3, A1, A4, doesn't matter. But PB means in the what is the like marginalized probability. Okay, you just see it what it is. It's not a big thing. You can go and find out what is marginalization and what is PD. You will get it. So Nidhi is asking what is the term VSHD denominator H. I told you that this is VSH means VSH comma D means VS means version space. Version VERSION. Version space means all those cardinalities that are consistent with the data. All those hypotheses which are consistent with the data in the space H, and the data is given by D. So this is it, right? You just see the lecture again. Okay. So finally we come to this slide. What at first you started with pH. At first you started with pH, and in that case there are like say 100 of hypotheses in the big space H, and every hypothesis was equally probable. So if you pick any hypothesis, you get the probability here. If you pick any hypothesis, you get the probability here. You can see that all probabilities are equal. So but once you see the data and you find out this hypothesis is not consistent, it gets zero. This gets zero. This gets zero. Let's say these hypotheses are inconsistent. So all the mass over these hypotheses will go away because this is zero. So of seeing the data using these hypotheses is zero. Using this hypothesis of seeing the data is zero. So because all the sum must be 1, so this mass get over here now. And it will get increased. The more data you will see and find out, okay, now for an example how these two graphs are different. So these two graphs are different. For an example, this was a true function, let's say. Sorry. So this is the data that you got. You have some hypothesis space in you. And let's say that hypothesis space is having a line, some quadratic function, and some cubic function. Let's say there are only 3 hypotheses. Now you get only 1 point. Let's say only 1 point. So when you get only 1 point, you can see all the hypotheses are fitting to it. Even line, if it is in this space, even line could go through this, even a quadratic function can go through this, even a cubic function can go through this. So all 3 are fitting to it. Now once you have 2 points, you see one more evidence. Once you see 2 points, again all 3 can fit. Once you see the 3 points, let's say, you can see that line is no more in a version space, because line cannot go through this. So the version space is restricted to these 2, because the quadratic can go through this and a cubic can go through this. So version space will be less now, because the more data you see, the larger version space will get restricted. Because this is the data set D1 I have seen. Once I see more evidences, let's say D1 and D2, some other hypothesis will go away from the version space, and the mass from those hypotheses will get mounted with the remaining one. So that's why this bar is increasing here, right? So in the example when H is consistent, somebody is asking, in the example when H is consistent, you said only 3 hypotheses would result in display of the data. Does it mean that either hypotheses are inconsistent? So The three hypotheses I am just explaining with by taking an example, sir. But if it is the case that in that example three hypotheses are consistent, yeah, does it mean that yeah, it means that other three hypotheses are inconsistent. The same thing again and again. Okay, so this is an important slide. Oh, how much time we left? So let me. How much time I left? 1, 2, 3, 4, 5, 6, 7. Okay, okay, okay. Okay. Oh my God. So this is important slide. Maximum likelihood and least recording is running, right? Yep. So now what we are trying to say here is that Bayesian learning, by using Bayesian theorem, we are trying to find out those hypotheses that are mostly probable, that can produce the data, like what is given the data, what is the probability of seeing the hypothesis, and given the data, whatever hypothesis is having a maximum probability, we are picking that hypothesis, and that is a map. So, are there any ways we can use sometimes this Bayesian analysis to find out sorry, we can use this Bayesian analysis to say that some algorithms that we use in learning is always producing the map hypothesis. I just repeat this statement again. It is important. What sometimes you can use Bayesian analysis. Bayesian analysis means the you are getting the H map that is most probable that after seeing the data. For an example, now somebody comes and give you some algorithm and see that this algorithm is giving me some hypothesis. Can you do some analysis on it and you say that because this algorithm that you are using is always giving me H map, that's why we can use it we can use usually very confidently, because we know that H map is that hypothesis which gives us the maximum probability when we see the data. H map is that one. And somebody is giving you some algorithm and say that just use this algorithm, you will get some hypothesis. If that algorithm that I'm using to learn the hypothesis is giving me the map hypothesis, then I'm very sure that every time I use this algorithm, I will get the maximum a priori hypothesis, HMAP. So you can use this Bayesian analysis in concluding or in mentioning some algorithms that yeah, you can use this algorithm consistently, because every time you use this algorithm, the only hypothesis that it will produce is always that hypothesis that is having a maximum a priori a posteriori HMAP. So I told you, I already explained this example in my previous slide, but with a different perspective we will see here that let's say I am having an algorithm, I am having some algorithm and I want to minimize the error in it. So let's say this is the true function. So this is the true function. In dark line and dotted line is like HML. We will come up with, so this is the true function that actually produced this data set. And how this data set, this is, if you recall the first chapter, curve fitting, I told you that there are some sinusoidal function and you may have some noise also. So that because the true point is this, but after adding some noise that is Gaussianly distributed, you may get this point, you may get this point, you may get this point. So this is the true function. These points that you are getting is after when you are adding some noise to a true value. So for an example, if you are using this x, so you are using this x, the true value that comes from the true function f solid line is this, but when you add some error to it, this will be this point now. Similarly, this is a true function when you use this x, When you use this x, you get this value, but when you add some error to it, this at this point will get shifted to this here. So now you have some function. That function is fx. You don't know about that function, but you don't know about that function. Every time you use this value fxi, you add some error to it, and finally you get di. So this is di. So for an example, this is first point, this is second point, this is third point, this is fourth point, this is fifth point. So this is d5, and my x is this x5, right? So my fx5 is d5 is equals to fx5. What is my x5 is fx5 is this value, right? So I am adding this value with some error. That error is Gaussianly or normally distributed with zero mean. So it means I have to pick some number with probability with the picking this value. This number is maximum here because its mean is zero, and picking this number is having the probability less than this number because the probability is less here. So I am picking some number from the normally distribution, and let's say this number is in the negative side of it because it is the true value is this, and it is decreasing this value. So obviously this is zero, this is positive side, this is negative side. So I must have picked the number from the negative side, and let's say this is that number. So this is this number with this probability, and this is negative in number. Now I'm adding this fx5 with a negative number, this number. So this is my e5. So it will shifted this true point to this point. So this is how I'm d5, my d5 is generated here. So likewise d1 I generated, d2 I generated, d3 generated, d4 generated, d5 generated. This is what is given here, right? So my maximum likelihood probability is the one that is maximizing this probability. It is nothing. So here my pH is like say equally probable. I assume that pH is equally probable, that every line is equally probable. So in that case, I am just maximizing the remaining expression PD given H. So what is the probability? What is the probability that given a hypothesis, I can see this data? So there are for every hypothesis, I have different probabilities. I want to find out that hypothesis that is maximizing this expression, right? So this is HML. I don't want to repeat it again and again, but it's the same thing. Okay. So the training example are assumed to be mutually independent given H. This is from the naive, you know what is mutually independent given H. It is the same assumption what we did in naive Bayes, right? Once the label is given, that everything is independent. So once the hypothesis, you know the hypothesis is, the every point is independent. So if there are 5 points, 1, 2, 3, 4, and you know the hypothesis is this. So this point, all these points, you can say this is independent to each other, right? So if they are independent to each other, it means the probability of seeing x1, x2, x3, sorry, d1, d2, d3, d4, d5 given h is equals to probability of d1 given h into probability of d2 given h into probability of d3 given h. You know this. We discussed in last class in naive Bayes. So if the training examples are assumed to be mutually independent given H. So because they are mutually independent, we can write these DIs in terms of product. So now this is the expression that I want to maximize it. So any hypothesis that is maximizing this product terms, that is my hypothesis, also my required hypothesis. Given the noise EI obeys the normal distribution with zero mean. So this is important point. I want you to be focused in this on this point here. So given the noise EI obeys a normal distribution with zero mean and unknown variance. So I don't know what is my variance, and but the mean is zero, right? Each DI must obey a normal distribution around the true function fxi. What does this mean? So my DI was fxi plus EI, right? So if this is normally distributed, I am just, for an example, every number I pick from that, I am adding x to it. So it is nothing but I'm just shifting my, if this was my zero mean, this is my normal distribution with zero mean, and if I'm adding number fx to it, it is nothing but just shifting this normal distribution to this location. If it's fx1 is equals to 4, let's say, so this mean was at first, this normal distribution that was 0. Now let's say this expression fxi is giving me 4. So this normal distribution is shifted to this location now, which is 4, right? So it is nothing but you have some number that is normally distributed, you are adding something to it. It means that you are shifting that number, shifting that distribution by this number. Now when you pick the DI, it is nothing, you can visualize it like this. If you would have picked the EI with zero mean, you could have the probability of picking this number or picking this number, but when you are adding something to it, you are shifting this distribution to some location that is given by fxi. Now you may pick this number, pick this number, and the probability of picking this number is very less, approximately to 0, because of this distribution. So what this point is saying, given the noise EI obeys a normal distribution with zero mean and unknown variance, each DI must also obey normal distribution around the target value of xi. I hope this is clear to you now. Because we are writing the expression for DI, because we are writing this expression, right? We want to maximize this expression, the product, we want to maximize this expression, and that is nothing but the probability of DI given H. We want to maximize this expression because we are writing the expression for DI. Given that H is correct description of target value, we can substitute fxi in respect of mu. What does this mean? So it means, sir, it means, because the normal distribution, when you were writing a normal, when you considering the formula of normal distribution, so when you were considering a normal distribution, oh my god, when you considering the normal distribution, you would have like 1 upon e to the power minus 2 variance x minus mu the whole square. So mu is replaced by fx now, because you're that fx, and fx is hx, because you are thinking that you are approximating your true function with some hypothesis in the hypothesis space. So you are replacing this mu with this hx, and this is the data. After simplifying this expression, I don't want to go into the details. After simplifying this expression, you will get this. Finally, the constant. Okay. So these are the expressions that you are minimizing. Okay, I will go step by step. So this is once you had expression, you take the log of it. When you find the expression that is logarithmic of that expression, that will be having the same value for maximum h. So now you are maximizing this expression. This expression is nothing but the log of that previous expression. Once you take the log of it, because this term you want to find out the maximum of it, it is a constant term, you can ignore it. You want to find out the maximum of this expression, what h is given max to it. Now, rather than finding the max of it, you just do minus of this expression and find the min of it. It is the same, right? So this expression is this now. So finally, all constant independent h can be discarded, and you will left with this hypothesis. So you get an expression, you get some hypothesis HML. That HML is that hypothesis which is reducing these errors. If this would be my fx, sorry, hx. So this is my e, this is my points, and this could be, let's say, my these are the same points I'm trying to draw here, and this is my other hypothesis. So this is saying that the hypothesis that is reducing these errors, the sum of these errors, is my probable hypothesis, because the sum of these differences are more for this hypothesis than the sum. Here the sum is less for this hypothesis. So the hypothesis that is minimizing this expression is my maximum likelihood hypothesis. And how I come by maximum likelihood? How I started? If how I started? I started with this maximum likelihood. Do you remember? I started that this is what I assumed. This is my maximum likelihood expression. How we got maximum? This is a Bayes theorem, right? This is the Bayes theorem, P D given H into PH upon upon PD. This was the Bayes theorem. Here PD is constant, I am ignoring. Here PH is equally probable, I am ignoring. So my maximum hypothesis is H map is equals to HML, and this is this. So I'm using this expression for maximum likelihood that this expression came from Bayes theorem, right? So this expression that comes from Bayes theorem. So this maximum likelihood is this expression. I want to maximize. I used these expressions here, and I put this data, and what I come up with, starting by Bayes theorem, I started by Bayes theorem, and I finally concluded with some expression, numerical expression. That expression is telling me that you have to minimize the error, sum of error. You have to minimize the sum of error. So I started with the Bayes theorem. Please listen this thing. Maybe you lost in that mathematics thing, but finally what you have to remember, you started with the Bayes theorem. You come up with some H map is with the multiplication of P D given H into P H upon PD. This is constant, you ignore it. This is equally likely, you ignore it. You are maximizing this expression, right? You are maximizing this expression PD given H. You assumed that every DI is mutually independent. Therefore, you did PDI given H and multiply because of mutual independence. So this was the expression that you come up with. Now you maximizing the expression. You put this probability. You put this probability PDI given H. What is that probability? Because I told you that you have that probability shifted by fx. You used some numerical expressions. You solved for it, and you finally got this expression. So this expression, you started with Bayes theorem. You finally got that we have to minimize the error, sum of error. It means Bayes was telling you to maximize that Bayes is giving you that hypothesis which is mostly probable. When you solve for that, you finally come up with one algorithm. So the other way what you would say, that if you can minimize the error, every time you minimize the error, you will get the hypothesis that is H map only. That's what the other way you can say. Okay, you just think over it. I will continue after the break so that we can have like 1 hour session now. So I will continue after the break. You just think over it, and I will repeat this statement for you after that.